So we start with Maxwell-Boltzmann curve. In the first example, we've been asked to look at a curve and on the same axis draw a curve for a lower temperature. This is a very common question. So what we're looking at here is we need to make sure the curve has roughly the same area underneath it. Total area is the same. The number of particles with energy greater than activation energy around this region will be lower. It'll be lower. Average energy will be a lower value as well, but it must mean that we have a greater area underneath the lower energy, so it all balances out. So the peak here, with the low temperature is higher. So explain the effect of lowering the temperature with what would have on the effect of the rate. Well, the rate will decrease. That's the first point. The second point, well, the first exclamation mark is that there will be fewer particles with energy greater than activation energy. It's always a good idea to think about this region here. So you can see fewer particles have energy greater than activation energy at any one point. Therefore, there will be fewer successful collisions in a given time. And 0.1.3, we've got another situation here. Second sample reaction mixture in the same reaction vessel. Deduce the change that was made to the reaction conditions. Well, sample 1, sample 2, you can see that the total area under the curve is less. We can see that in this situation here, area underneath this curve is lower than this one. The total number of particles has been reduced. Therefore, the explanation of the effect is that the rate will decrease. And the reason for that is because the particles are going to be further apart. If we're talking about gases, the particles are going to be further apart. Or if there's fewer, the number of molecules reduced, there's going to be fewer collisions anyway. So again, this very important word of successful collisions, and what I didn't state in 1.2 was this phrase here, in a given time. Remember that rate is the change in concentration over change in time. We've got to mention this phrase here. So it was certainly mentioned in the first question, should also be mentioned in the second. And notice the underline here of successful collisions, not just collisions. Remember, collisions can occur but not always be successful. New question 2.1, draw the skeletal formula. This is where you just show the backbone of the molecule without showing any C's or H's. And this you need to show 2 branch isomers of hexane. I've drawn all 4 of the isomers of hexane. So we're looking for chain isomers. You can see that they've got 5 carbons in the chain here, and 4 carbons here, 4 there, and 5 carbons in the chain there. Every point of this diagram for the skeletal formula is a carbon. There's a methyl group coming off here. It's chain isomerism. You might say structural isomerism. Chain isomerism is a type of structural isomerism alongside functional group isomerism and positional isomerism. This next question, 2.3, we're thinking about an engine which is partially blocked by debris. What we're assuming here that it's carbon. Remember, incomplete combustion leads to the formation of soot. Now, if there's incomplete combustion, it could also be carbon monoxide. So when you're writing the equation that's taking place for the combustion of hexane, what could be accepted is either carbon or it could be carbon monoxide. And here I've written the equation for the formation of carbon monoxide. Balanced, all equations must be balanced. Never write a word equation, it's always going to be a symbol equation. In this case, you didn't need to state symbols. Suggest how this partial blockage might affect the performance of the helicopter engine, so 2.4. Well, if it's in complete combustion, then the first point is there going to be less energy given out by the fuel. The engine is going to be less powerful if there's less energy. Other answers were also accepted.